So think about variables. There's no dynamic memory allocation. There's no new. We'll talk about new later, but there's no, because that makes pointer analysis much more complicated. Only variables, that's all that we have, and we can take the addresses of variables. So this y can point to a whole bunch of variables. It can't point to the heap. It can point to a whole bunch of variables. And let's suppose that I have a pointer analysis which gives me some points to information. So in particular, it tells me what the set of variables that y may point to. So I have a points to information which is called may point to, and I can look up y, and that will give me the set of variables that y may point to. So what can I do with that? How can I do better now? So what do I include in y? Yes.
You want to make sure that all the variables y can point to have the same kind of thing.
So I want to make sure that the only way I can know that x is a constant is if all the variables that y point to are a constant and the exact same constant. And if that happens, then x could be that constant. And so what we could do is, we could say it formally like this. The only way I can add that x is some constant n, so I can add the x arrow n, but I can only add this thing if I have that, basically, how do I say this in English, that anything that y points to has a constant n. How do I say that? Not in English. I said it in English. How do you say it formally? Yes?
You can take the intersection of sets n such that if c is in may point to y and it points
Wait. So C.
or, well,
No, C. Right. No. So you said C. That's good. So C is in may point to y.
Yeah.
So C is a variable. So let me call it V instead, just for naming purposes. So we know it's a variable because our naming convention is important here. So V to C may mean you think it's a constant. So basically, you're saying V is going to range over all the things in may point to y. Okay. And then what?
And we take the intersection both of the things that are pointed to by v.
Right, so that's one way to do it. There's actually a slightly simpler way to express it. I think that works. I think there's a way to get that to work. But there's a slightly simpler way to think about this. Does anybody want to take a crack at it? There's actually, first of all, what do we need? So this V has to range over all the things that y may point to. What's the kind of mathematical operator that allows us to do this kind of, to range over a set of things? What? What?
We don't?
Well, there's okay, so you're right. So basically we're going to say V belongs to may point to y. Yes?
Universally quantify over it and then have it equal n.
Universally quantify. So for all V in this may point to y,
They all equal n.
they all equal n. And how do I, so every V has to be equal to n. So how do I say that? Do I say V equal to n? No, right? So how do I check if something is a constant? Right. So V arrow n is in the input set, right? So basically this says, basically for every V in may point to y, V arrow n has to be an n. Right? And this is a way of doing it without the intersection, right? You can do the intersection too. Cool.
Don't you mean that v points to n as in the, you said for all v, but in may and I, that v is equal to n in the input. We have x points to n, I'm not sure I understand the connection. Between the...
Yeah, so the connection is this. Basically, I'm saying that I can add the information that x has the value n.
Yeah.
So the way that you read these sets is basically you create this thing such that this condition holds, if this condition holds. So basically I'm adding the information that x is equal to n if for any v that y may point to, v is equal to n on the input. Right? So v, if anything that y may point to, if for any v that y may point to, v is constant on the input, then x is constant on the output, and equal to that n.
So in other words, we could say for all n, such that there's a v pointing that n in the input, and that that v is also in the may point to of y, then for all such n, we can assign x to n in the output.
Right. I mean, that's what this thing says. But you have to make sure that you also quantify over v. It has to be for all v. Just make sure. I mean, that's the important thing. One of the most important things is that it has to be for every. The key thing is for every v in this main point to set. It should hold.
I don't think the for all n makes sense because there should only be one n as your point. All of these should be to a single n, right? Because if it may point to, let's say v1 is going to 5,
right, I
v2
mean,
is
sometimes
6.
in this case there's only one n, but the truth is that when you write this down formally, it actually really says build this for every possible n, because this n is a free variable. It says if you find any variable n for which this works, then do it. And in fact, in fact, it is possible theoretically for one variable to have multiple.
In constant propagation?
Yeah. We'll talk about that. Yeah, it's possible.
Okay.
I know, it's weird, isn't it?
It seems not constant, but okay.
Well,
If, like in the last example, we said a was 5 and we changed it to 15. If a could have been 5 or 6, then we're changing it to a is 15 or 16, for example.
right, so the question is, what does it mean, what does this piece of information mean? All right. So, I'm going to defer this discussion for just a little bit until we define the lattice more carefully with top and bottom.
Okay.
But intuitively, if you think of the semantics of this, if you actually if you get this answer at fixed point, that means you finish the analysis and everything's a fixed point and you got this answer. What this means is that the actual is unreachable, right? I mean, it just means that you have this is an inconsistent, piece of information. It means that x is 15 and x is 10, which basically means that it's just that piece of code is unfeasible. Like it's infeasible for you to get to that point in the program. We'll see that that actually these things are very, very important during these kind of steps are extremely important during the intermediate steps of the analysis. And we'll get to that in a second. I'll explain when we actually see the full lattice. But you're right that in most cases you will just have one n. So the important quantification is the for all v. Any questions? Any other questions? So okay, what about this statement? Oh boy. How do we give up here? So let's think for a second. Let's say we don't have a pointer analysis. Because remember what we did first, we said, let's say we don't have a pointer analysis. This is our version of giving up. We just said, you know what, I'll just remove it. So let's say we don't have a pointer analysis. What do we need to do to give up? Yeah.
You have to make it off. You have to return the empty set.
Right.
So this is a really, right, well, first of all, it should be clear that the empty set is always okay to return. So even here, I could have just returned the empty set. In fact, if you really want to give up, you can just always return the empty set. The empty set will always be okay, because you're just saying nothing's gone. I mean, it's like you're giving up totally. But here, the reason why, if we don't know anything about x, it's kind of a weird thing, right? Here we knew what was being modified, right? So it's very important when we're doing this analysis, we really can't miss any things that are being assigned, right? Because if we somehow miss that there's an assignment, we may actually have some information that tells us that something is constant when it's not. So we need to really make sure we remove anything that could possibly be modified by this statement, right? And so the simplest, the if you don't know anything about x, you have to literally remove everything. Does anybody see? There's no other thing. What else could you do? I mean, right, I mean, if you somehow wanted to maintain some information here, let's say that, I don't know, something is some constant, I mean, you have to somehow know that this x didn't modify this thing. Because, right, I mean, otherwise it's just, it's kind of a weird thing. Although, actually, it's not totally true. We'll see in a second. There's actually a clever thing you could do, which is really clever and mind-bending. It's going to hurt your brain, but in a very pleasant way. And we'll see. It's actually very mind-bending. There is one thing you can do, which is really, really weird, even though you don't know anything about x. You guys want to see that first? Should we do that first?
Sure.
Using some variables equal to y.
No, I mean, how can we do better if we don't know anything about x? How can we do better than just the empty set? Right? Let's say we have no information about x. How can we how can we propagate how can we get any information going through this statement?
You mean if we don't have must point to?
We don't know anything about x. You have no clue. You have no information about x. Yeah.
You can say
Y is still a constant.
Okay. Okay, so hold on. So if y is still constant, okay, and then what? Wait, so if y is still, okay, then what?
It remains constant, right? So y still.
What is x? Okay. So you're saying if y is a constant before, so you're saying that is that what you're saying too?
Yeah.
What's the reason behind that? How can you argue that this is correct? Yeah.
So if x doesn't point to y, y remains the same. If x does point to y, then you're just deciding against itself.
Right, so basically, so you know that y is equal to n before. If x does not point to y, y doesn't get modified, so y remains equal to n. If x does point to y, this is self-assignment, right? And this self-assignment doesn't do anything. Okay. Yeah. Huh? A constant? A constant can't have an address, no. No, a constant is a constant, it doesn't have an address. What?
sure can.
Wait, what? No. Even in C, I think if you do address of 5, it will break. Unless someone wants to, huh?
I think it adds the constant into the static
What?
part of memory, and then it
That's
addresses it.
ridiculous. Wait, what does it do? It creates a block of memory for it?
Because imagine for anything that's not constant propagated, it has to somehow have a variable somewhere in the
That
code.
sounds awful. I don't know
How would
why-
you do x, which is a non-constant, plus 5 in your code? If you didn't, I mean, that has to be handled at runtime because you have to read x.
Oh, no, I know,
So it
but
has
I'm
to
saying
do
the C code, if you address to 5. Oh, you know what, but yeah, it's kind of, anyways, let's just, you know what, let's assume for the purposes of, the beauty of this is that we don't deal with C. We're dealing here with an intermediate representation, and I can just claim, and I'll tell you, it will become very blatantly clear on the next slide why we don't want to deal with the full C, why we don't want to have our own language for doing this. But let's just assume you can't take constants. Yeah. Do you have a question? No. So, okay, this works. There's actually a slight generalization of this, which is, there's actually a slight generalization of this, which is that you can actually do even better than this, which is you can do the following. Oh, sorry. Wait a minute. So, y is, so I'm not going to do y, I'm just going to do z. So I'm going to pick some other variable, not y. It's some other completely different variable.
Alright, so all z n as long as y
Such
points to n.
that this is instead and
Y goes to n.
right? So this is like really weird because it's like some completely random other variable. It doesn't even appear anywhere. It's like some completely, totally other thing, right? So if z, if you have some other variable that has nothing to do with this statement, which is z goes to n, and you knew that before the statement, then basically what happens is in this statement, right, so you know that z goes to n right before, and you also know that y goes to n. So basically both z and n and y are n. Then what happens with the statement? Right, either x points to y, no, sorry, either x points to z,
Or it doesn't.
or it doesn't. If it does point to z, then this assignment basically takes y and puts it in z, and therefore I know that z is going to have the value n afterwards because y has the value n, right? If x does not point to z, then I know that z already has the value n, so it'll get preserved. Is that mind twisting? It's pretty cool, actually. It's actually really interesting, right? I mean, you have this information that gets preserved through this assignment. I mean, think about it. You have this information about some random other variable that gets preserved through this assignment, even though you have no clue what x points to. You have no information about what x points to. The key is that what you know is that y basically has a value n, and you also know that z has a value n. Yes?
We don't explicitly relate it to x.
What?
Also, we said that x may point to z, but we...
Well, no, this is not point to information. This is just, let me write it differently. Let me actually write it differently. So, I mean, this is not point to information. This is my constant prop information. Right? So this is that, this is just saying that x has a value n. Okay? So basically what I'm saying is, if y has a value n before, and z has a value n before, then I know that z is going to have the value n afterwards. Wait, let me just write it this way. Right, this is basically, if I know that z is equal to n and y is equal to n, I can learn that z is equal to n afterwards. Does this make sense?
What if,
Regardless of what x points to. Weird.
what if you had the case where we just mentioned in the last one where like z is n1 and z is n2, where n1 is not equal to n2? Because you said we can have the same variable point to numerous other variables.
Yeah, so then you'll get multiple z's on the output, right? And so
Well,
z equals
shouldn't we
n-
be trimming it though, according to this definition on the right?
Oh, you're only trimming it based on you're saying if you have multiple values of z.
Yes. Then over here we're going to actually be stripping one away.
Right. So yeah. So really, okay. One way to think about multiple of these bindings when you have, so you're saying, you know, this.
Mm-hmm.
So one way to think about it is like this, is that, you know, when you have no binding for z, that's not a constant. When you have one binding, it's a constant. When you have multiple bindings, it's a super constant. Basically, it means that you can assume that it's constant, and you can pick which constant you want it to be. Like at one time, what it means is that if you get, like you can just pick whatever of these constants you want, whichever one makes your optimization better. And so in this case, what it really would do is that it would just kind of
Force to the one.
allow you to pick that one to get the better results on the output.
Okay.
But that's one way to think about it. It is a very weird thing to think about these cases where you have multiple constants, and we'll get rid of that very soon because it does get intellectually very. As you're noticing, it's kind of like, wait, it's kind of weird. But okay. So this is an interesting thing, which that we can basically do in union this, right? But okay, so this is if we have no pointer information whatsoever. So what about if we want to? So let's talk a little bit about if we have some pointer information.
Like must point to?
So let's say we have some pointer information. What do we do? Yeah. We have to do. Yeah. What do we do?
Do we have must point to?
No. Okay, fine. We got must point to. So, no, let's assume we don't have must point to.
Okay.
Actually, must point to will not help you in this case.
If we know X point,
Well,
must point to
it will
something.
help you in some. So yeah. So if you know what X points to, if you know that X points to only one thing, sure. But what if it doesn't point to just one thing? You still have to be able to handle this statement correctly, right? So let's not use that as a crutch for now, because we need to. So our goal is we need to make sure we remove any possible thing that this thing could actually assign. Because otherwise, if we miss one of them, then we're going to be in trouble later on. We're going to conclude some constant information that's not correct. Yeah. What? Well, so this is, I mean, we're not doing, so this is not, the main point you set for X is constant. It's been pre-computed. We're not going to change it right now. And actually, this is not, the main point you set of X will not be changed by this statement. We're not changing X here, we're changing star X, right? So, yeah.
We can take out all the variables assignment in main point to X.
Okay, so we can take out everything that X may point to. If X may point to something, then we better remove that thing, right? So how do we do that? I don't even know how to write this, but I guess I can just write it like
Use V or something. Use V. Mine is V arrow.
Oh yeah, V arrow star such that Z is may point to X. Okay. Now, in fact, let me point out that this is actually, this step is crucial, okay? So, I mean, I skipped some steps here, but so I kind of did things in a different order, but let me just be very, very clear. When you do the empty set, that's fine, okay? If you do anything else, you need to have this step. Even in the case where we actually did that union, remember when we did that union with like, oh, Z points to N such that, Y is N and Z is N in the input set? We still need to do this removal before we do this. This is the stuff that adds information, but we still need to make sure that we delete everything that X may point to. Okay, because if X may point to something, we still need to make sure that we're removing that information. Because otherwise, we actually could lead to wrong results, right? We could have something where X could point to a variable that was constant before and we just forgot to remove it. So this is crucial that you basically make sure that for your analysis, you have to remove all the things that are, in some sense, killed by this statement. There's kind of this thing that we're going to talk about later as well, which is these kill sets. This statement kills a whole bunch of information. It seems very violent, but that's what. And we need to make sure we kill all the information that we're supposed to kill. Okay, does this make sense? This part of it here? Yes. Okay. And now, I mean, you could, so we could do that trick. With the Z equal to N, we can also do the trick that you're saying. I mean, if you know that X points to one thing, then you could basically, kind of do something special. And you could basically say if X points to this one thing, then it's really just an assignment, almost like an assignment to that one thing. And you can write down the rule for that. So that's what it looks like then. Basically, you remove everything that, any binding where that Z may be, that basically X may point to Z, right? That Z is a may point to set. This is the one we had that we came up with at the very beginning, which is this weird one where Z goes to N. You have it before, and then you basically have the Y and Z, you have the Y and Z before, and you can set the Z after, and then you have this one here, which is a must point to. All right, any questions on this? So, oh no, seriously? Oh. Okay, what do we do now? Okay, let's button down. What? What? We give up? Okay. So there's there's three ways to do this. One is to give up. Let's think about a better way. Oh, and actually there's four ways to do this. One is to give up. The other one is to literally die trying to do this. But we don't want to do either one of those. So what can we do that's easy? That's really easy. So if I told you to analyze the statement, what would you do? Given what we've written on the previous slide. Yeah.
We still have to remove everything that X.
Sure, we can do that. But I wanna take a different approach.
Recursive calls.
Whatever the X.
Sure we can do that, but I want to take a different approach. That just makes it like it's just really, really easy.
Recursive calls.
Okay, what does that mean?
We already have a dereference of X equals Y. Well, we could do that with the Y and the Z, and then drop that into the prior thing.
Right. So we already have flow functions for basically the previous, on the previous slide we have X star Y, we have star Y gets this, and we have on this here we have the we have this thing, right? So basically what we can do is we can write a small program, transform this into a small program that basically has a temporary in it, actually two temporaries, where basically we say T1 gets star Y, T2 gets star Z, and then you do then you do star X, then you do T3 is equal to T2 plus T1, and then you do star X gets T3, right? So and then we can just apply our flow function kind of as it's basically the composition of these things. We just pass it through all the stuff. So that's another approach to doing this, okay? Which is actually much simpler, because in some sense we've already defined the flow function before. And okay, so then there's an even more extreme direction, which is to basically not have the statement at all. Okay? Just say this is not part of our language. If you want, so if you have this kind of statement in your source language, then you have to basically translate into a whole bunch of small instructions of the kind we already had, because we already covered all the basics in all the previous instructions. So notice how this is very important. This is why we don't want to analyze. This is why we want to analyze our own intermediate language and then translate something like C or C++ in our own language. Because in our language, every time we add a new statement, we have to add a flow function for that kind of statement. And so we like to keep our language very small with a small number of statements, so that we only need to write the flow function for our core statements, and then we translate the semantics of C into a combination of the things that we define. Right? This is a great example where there's no point in writing the flow function for this, because we already did it. By the previous slide, defined everything there is to know about how these pointers work and how this plus works. Okay? Okay, does that make sense? Okay, now what about calls? So calls, we have no clue. We really have no clue. So we're just going to give up for now. And we'll see later on that there's other things you can do. So just to give you a yeah.
like, when it's convenient, you can probably also do something and, like, for example, when say that things can happen, so they're like, find a list so that we can think in the correct sense.
Yeah, I mean, if I ask you a problem on the midterm, I'll try to make it clear. And usually I would not give you the cases that I don't want, like, for example, in this case, it's pretty, let me put it this way. We have not seen, if I ask you to write a flow function for this, given the material that you've seen so far, what would you do? There's nothing you could do, right? Or maybe you can do something. What would you do?
If none of the arguments is a pointer, then it will be fine. Like you don't need to remove those arguments because it's part of arguments. So if the arguments are y and z. Then y and z will still remain.
Absolutely. So let me clarify what I mean. So actually this is great because it actually matters what your function calls are like in your intermediate language. We can have function calls be functional, which means that they don't change the state of globals, they don't change the state of locals and other functions. They just take some things and return something. But if all my variables are global, and this G, or possibly global, and this G is allowed to make writes, is allowed to modify global variables, then you would lose all information. Another way to think about it is that if G is global, sorry, what am I saying? If G can only modify globals, then basically what you could do is you can remove everything from the input set that is a global. So you lose all information about globals, but the locals you retain information about. Right. And we'll see later on that there are actually ways of doing various kinds of analyses on G to figure out all the variables that it modifies. So even for globals, we can basically compute the set of variables that G modifies, or that G may modify. And then we remove only the variables that G may modify, right? We don't remove all globals, we remove only the ones that G may modify. So I think the answer to your question is, part of the thing is, there's a huge spectrum. We want our analysis to be correct. But given, for analysis to be correct, there's a huge spectrum between precision, right? So, I mean, ideally you'd like to have your analysis be as precise as you can make it when you define these things. Obviously, if I return the empty set here, when there's clearly a very simple way to kind of invoke the other ones, that's not what we're trying to learn. But in general, this is actually one thing that you will face in reality. You will always have a choice of being more precise or less precise within the confines of correctness, right? Within the confines of what is correct, there's a spectrum of how precise you can be. So that's just the reality of how this works. That's just reality. Okay. In fact, this is again a great example of this. This is an example. So, what do I do here for conditional? So I have some input information coming in here. What do I do? What do I spit out on the other end?
Are we assuming no assignment?
No, sorry, no assignments. No assignments in here. If there's any functional, yeah, absolutely. Because here you can say, oh, what if this is a call like G or something? No, we're going to make the call outside. We're going to handle all the G-ness outside, and then we're going to handle all the if-ness in this case. Right? We're going to separate. That way, the idea is that every flow function handles kind of a really core concept, and then we kind of can combine them together. So no assignments here. So if there's no assignments, what's the simplest thing to do?
Copy.
Copy. You just copy this thing, it just comes out. Now, here again, you could be a little bit more clever. So what's an example where maybe you can be a little bit more clever, where you can get more information?
If you have if x, then you can assign x to like true or x to false.
Right, so if I'll take a slightly different example just because we're talking about numbers here. But if I have, something like if x equals to 5, then on the true branch, which, let's say it's this branch here. This is a false branch. This is a true branch. I can add x equal to 5. Okay? So notice how there's no assignment that actually caused this information to come in. This is just information that comes from the fact that I went down this branch. Okay.
Although if we're doing constant propagation at that point, that's where we just drop off the other one, right? You can't be false then.
What?
If x would constantly be 5 there.
No, oh yeah, well that's a different story, right? So
Never mind.
wait.
Never mind.
That's a different story. Hold on, you're saying what happens if I know that x is 5 here. That's a different thing. This is if I have the information that x is 5 before, then I can basically say that this is like an unreachable branch. But what we're talking about here is different. We say you have no information coming in possibly about x. And then you're just gonna, well actually what you do here, is, actually you have to be a little bit more, if you really want to do this, you have to be a little more careful. This is kind of shows all the subtleties that come in. What you have to do is you have to say, is x mapped to something on the input? If it is, then check if it's 5, right? And if it is, then you can keep the 5 on this side. If x is mapped to nothing, then I can add x is 5 on this side, because on the true branch on those 5. So, okay. Cool, what about merge? What do I do with merge? So merge is when you have two pieces of information coming in from two different branches, and what that means is I can either come from this side or from this side, right? It's a piece where the execution comes here or here. Yes?
Like intersection.
Intersection. And the reason why that is because let's say I have x is 5 here, and on this side I have x is 5 and y is 10. Because let's say on this branch, this is a branch, and that's another branch, and here we had x assigned to 5, here we had x assigned to 5, and y assigned to 10. So if we do the intersection, we get that x is equal to 5 because x was 5 on both sides, but y, we get nothing for y because y was 10 only on this side, it wasn't on this side. So basically, you can only get information about x being constant if it's that constant on both sides, right?
Okay. What if the value of x is different on both?
Yeah, then it'll be the empty set, right? I mean, then it's the empty set. Meaning that you don't get any information about x, which is exactly what you want. I mean, if x is assigned to one value here and another value here, you merge, they're different values. We don't want to learn any constant information about it. And notice, by the way, we had this question before at some point, this is different from execution of the program. This is when you execute the program, right, means we're losing information here. On this side you have x equal 5, on this side you have x equal 10. We're going to lose information about x here. We know nothing about x anymore. So it's actually very different. This kind of analysis is different from actually literally executing the program. So okay, what's the lattice? What does the lattice look like? So we talked about how the lattice is this big set here. Right, so the D, what's the D? The D is to the power of what? I'm going to call it the all set. And what is all set? It's basically so what is the ordering on the lattice? So let's take top and bottom first. That's the easiest thing to pick. So what's top and bottom? Remember, top is the most conservative answer. Bottom is the most optimistic answer. So top is the answer that you can always return in a pinch. It should always be correct. What? Empty set. So top is the empty set, and that usually kind of sets everything up. Oops, sorry. That usually just sets up all your lattice. So top, so what's this then? Bottom is what? It's a full set, right? So basically, it's this set It's this massive set of all the constants mapped to all the variables. So, okay, what about the ordering here? So, what's this thing?
Join.
So we have like this. So when we do this, we go up in the lattice. So it's basically you have two elements, and you go up like this. So what do we do to go up like this? Intersection. And then this thing is union. And notice how a lot of times at merge points, it's in most cases, not in all, but in many cases, the merge nodes are always going to be a join. And in this case, the join is intersection, as we saw previously. So the merge node, that's what we did, we did intersection. And then the ordering here is going to be, the ordering of precision is like this, right? How is it? It's superset, right? Is that right? Wait. Yeah. Right, because basically what we want is lowering the lattice is more precise. So lowering the lattice is more precise. And lowering the lattice is bigger set. And bigger set is more precise, right? We have more information about constantness. So bigger set means more constantness that we can learn. Okay, does this make sense, the ordering on this lattice? Okay. So now let's try to run it on an, oh wait, what happened? Let's try to run it on an example to see how this works. So we start off, so our analysis starts off with everything being bottom, right? Every edge in the control flow graph is bottom. Okay, so basically everywhere we have here, we have bottom, and what's bottom? Bottom is that full set. So see, this is where bottom comes in. This is where you actually have these things happen in practice. You have these full sets of everything. Conceptually, you have this full set of all possible constants. And on our entry node, we're actually going to set the top, which is basically going to be empty. On our entry node, we're just going to say we have no knowledge about any constants at the input. Okay? So there's no constantness of any variables on the input. And now we're going to run our kind of data flow analysis. So how does our data flow analysis work? It takes a node, it puts all the nodes on a work list, and then takes a node off the work list, analyzes that node, and then puts on any other nodes that have modified on the work list. So we're just going to start off with this node, and so what do we get here? We get the set x goes to 5. Right? What do we get here?
I think that's a 2.
Now what happens here is we have a merge node, not a merge node, a conditional node. So we run the flow function of this conditional node because its input changed, right? The input is no change, so we do a flow function of this node. What is it going to do? It's going to push both information on both sides, right? So we'll get on both of these sides, we'll get, cool. Okay, which one do you guys want to do first?
The right one.
The left or the right?
The right.
The right, okay, let's do the right. So what happens here? So it's the same information as before, I'll just do it like that. 3, what happens here?
Y gets 10.
I guess we have the same information as before, and then what do we have? Y and what?
10.
10. And so we have exactly the same information, but we have also, this is 15. And so this is now, this whole piece of information which has X5, V2, W3, Y10, Z15. That's this whole thing here. And remember here we have a merge node. So what do? Should we run this merge node? We could. There's nothing that prevents us. We could run this merge node and do all that, but we know that we're going to have to rerun it anyways because this is going to change, quite possibly. So it's probably better to do this stuff first. Okay, now, this is where something really spectacular is going to happen. Are you guys ready for it? Do you see, okay. So what's going to happen is that we're going to do this in slow motion. There's a merge node here, right? So what does this merge node do? It basically takes the two inputs and it does join, which in our case is intersection. Now, what is this set? What is bottom?
Everything.
Bottom was a full set. It was this massive set of everything in it. So if we take the intersection as this massive set with this thing, what do you get? You get this thing. Okay? So in fact, what you get right here is you get x goes to 5 and y goes to 2. And another way to look at this, just one second, another way to look at this in a more lattice theoretic way is that what we did is we did bottom joined with something here, okay, with some v. And bottom joined with something is always that something. If you think about it, because you have bottom and you have this thing, right? So what does this operator do? It gives you the least upper bound. So what's the upper bound of these two things? Is v, and that's the least one. So it turns out that this is why this is happening, because bottom joined with any v will give you v, and this is exactly what's happening. We've basically taken this thing, and it really what this thing did is it kind of let all the information go through from this side. So notice, okay, great. So what do we do next? So now this information is at this edge. What happens is that now this statement needs to be analyzed against this information change. We used to have bottom on this information. Now it's not bottom, it's something else. So we have to analyze, and what do we get here? Okay, so this is also a very important lesson here, a very a learning moment here. Notice that we have just concluded that x is equal to 6 here. Boy, is that wrong, right? X is not equal to 6 here. In fact, there's this loop. This loop, it's x increment every time we're on the loop. This is not going to be 6. If we stop our analysis in the middle here and conclude that x is 6, it's totally wrong. So you get another example and showing you very clearly that you can't stop in the middle of your analysis. You have to keep on going until you finish. So now what happens? What happens?
Set W.
So now x goes to 6, and here
V2, W3.
Okay, so now this information gets passed here. So this edge gets, oh wait, no, hold on.
You pass it to both.
There's another node here. Right, so this information gets passed into this branch node. And this branch node will then push this information here. Once this information is pushed to these two edges, we have to push on the work list this node and this node. Should we analyze this node?
No.
No. We could if you wanted to, but we probably will have to reanalyze it later because we haven't yet finished with this, and so this answer will change eventually. So we're better off analyzing this node. So if we analyze this merge, now what happens?
You lose X.
So this, right, so now we do intersection, and on the second iteration, right, so this was the first iteration. On the second iteration, we intersect this with this. And what do we get? We just get v goes to 2, right? Wow, that v variable is pretty, it's persistent, right? It's awesome. It survives. It survives. It survived this massacre. I mean, X got totally butchered. It got removed. But V was able to survive. And so now we go through again. What happens? So if we go through again, what do we get here? We get
V2,
V goes to 2.
and you get V2, W3.
And X doesn't get anything, right? And then we do V goes to 2, and then W goes to 3.
Why doesn't X get 1?
Well, because there's no information about X. We don't know that X is 0. If we knew that X is 0, then we would get that X is equal to 1. But X, you don't know, if X is not a constant, right? If X is something that varies through the program, I can't make this, I can't conclude anything, and that's how our flow functions work, right? Right. So now we have this V goes to 2 and W goes to 3. So then this gets placed on this edge and on this edge. And so the input of this node and this node change. So we put both nodes on the workplace, but we're going to analyze this one again because we want to make sure that we finish with this loop first. So now what happens? We have V arrow 2 and W arrow 3. So we analyze this merge node, and what does it give us?
Same input as last time.
It gives us V equal to 2. So we don't put this node on the work list, because we've already analyzed this node with this concept of VR2, so we don't add this thing to the work list. Okay? So instead, what we do is we have to go back and say, what else is on the work list? Well, this node is still on the work list. We added it several times, actually. But now, finally, we're ready to process it. And what's the information we have on this edge now?
V2, W3.
V2 and W3. And now we do we have this merge node, which does this intersection. And what's the intersection going to give us?
W3.
And V2. We have V2 here.
Oh, yeah.
It persists here. Cool. And then what this shows is basically you can actually simplify this thing. Right? You basically both of these is 6 basically. So notice that what's really interesting here is that we were able to correctly figure out that X here varies across the loop, so we didn't figure out anything about this X. And we were able to correctly propagate this V equal to 2 on both sides, both through this loop and through this non-loop path, and maintain that information all the way here. And notice how we're not executing the program. If we were to execute the program, this would keep on running possibly forever. We would increment X every time. We would figure out, oh, X is 0, X is 1, X is, no, actually, sorry, X is 5, X is 6, X is 7, X is 8. But we don't do that because of this intersection. We eventually, as soon as we get X is 5 and X is 6, X disappears. Okay? Okay. Cool. Does that make sense? Okay. So let me do, let's do one more example. The reason why I want to do this example is because I want to show you what happens when we, I'm going to do this example starting from everything to bottom, and then we're going to do this example again starting everything at top, to basically show you how, so we actually had this debate of, should we start bottom, should we start top, which one gives you better answers, etc. So let's take a look at an example that shows us the difference between these two. So again, we're going to start here everything at bottom. So everything's going to be bottom everywhere, and we're going to start this being the empty set. So basically this is going to be X goes to 5. This is basically X goes to 5 and A goes to 15. Now, again, this is the empty set. No, it's not. This is a full set. And then we do intersection of this full set with this thing. What it means is that this information goes through. So basically we get that X is 5, A is 15. What do we get here?
X6.
X is 6, A is 15. What do we get here?
5.
X is 5, A is 15. Then we come back here. Now we do intersection, and we get the same thing, and we reach the fixed point. So we're done, okay? And then basically that means that this answer here is this X is 5 and A is 15, and therefore we get here basically that X is 5, A is 15. Okay. Cool. So let's do the same example, but we're going to start everything at bottom. So, sorry, not at bottom, at top. So remember, when we did our optimistic iterative data flow analysis, we said that we start everything at all the edges at the bottom, and we keep on going up. And we thought there's another way to do it, we start everything at top. And so, in one approach, you start at bottom, you keep on going up. The other approach, you start at top, you keep on going down. And if you start at bottom, bottom is always incorrect, and you're inching your way forward towards correctness. Whereas with top, you always start with something that's correct, but you're basically getting more and more precision. Well, let's say we start here with everything being top. Every edge is top. So what's top? Top is the empty set. Okay? So now we have the empty set everywhere. And the most important one is on this back edge. So here, what are we going to get? We're going to get X goes to 5. We're going to get X goes to 5 and A goes to 15. Then what happens here?
You union them?
Wait, I do what?
Don't you do a union?
You want me to union them?
Is that what we did before?
No. Wait, hold on. At a merge point, before we did intersection.
I mean, before when we did our whole work list, like the algorithm, we said if you start at bottom, you do...
No. The flow functions have to remain the same. Otherwise, you're going to get into really, really wacky answers. I mean, for constant propagation, you can't. I mean, if you can't do that. No, you can't. That would be. I mean, that would just totally be wrong. So let me give you an example. I mean, suppose I have a program like this. Okay. And that's it. And I'm doing optimistic. I'm starting everything with the empty set everywhere, right? I'm starting everything at top. I mean, if I do X gets 5 here and Y gets 5 and I have a merge here and you union them, then you're going to basically say, oh, well, X is 5 here and Y is 5, which is totally wrong. Neither of those facts is true.
Right.
So we can't merge nodes, still have to do intersections. We can't get away from that. But now you see where the problem is that now this intersection is going to give us the empty set here. And now, basically, this entire loop is basically going to be stuck at the empty set. I mean, we're going to get the empty set here, we're going to get the empty set here, then this is going to get stuck, and we're literally going to lose all of our information going down. Okay? So, this analysis basically got everything empty set everywhere. That's what the fixed point is, that's what the final solution is, except we have X goes to 5 here. So we can still learn that X is 5 here. So it's not like we don't get any information, right? We did get the information that X is 5 here, so I can transform this to A goes to 15. But this X, I totally didn't get. I wasn't able to figure out that X equals 5 here, whereas in the previous version of it, I was able to figure it out. Okay? And crucially, the important thing here is that what optimistic iterative data flow analysis allows you to do, what the optimistic version allows you to do, is allows you to enter a loop and keep this information that you have from the top of the loop. And basically say, you know what? At this point, I don't know if X is going to be 5 and A is going to be 15. Because it depends on what comes here. But let me assume that maybe this is going to be the best possible information for me. And that, let me just assume that it's actually going to be X is 5 and A is 15. And then I'm going to do all this stuff, and if it turns out it's actually consistent with it, it's okay, right? And that's exactly what happened with this stuff here too. when we came down this loop, we kind of assumed at the beginning, look, x is 5 and b is 2, which is totally wrong, actually. At the end of the day, when we finally solved our problem, x was not, wait. Yeah, I mean, x was not 5 here. At the end of the day, x was not a constant here. This is wrong information. So in optimistic data flow analysis, when we start at bottom, you're allowed to basically go through incorrect answers to get to your solution, which can lead to better answers than if you force yourself to start at top, as in this case, where we basically lose all this information because of this empty set. Okay, do people, yes?
But does it allow us to stop anywhere?
Yeah. This, you could stop anywhere here, right? Because every time we concluded information in this thing, it was guaranteed. Right? I mean, the only information we conclude was this, x equals 5, which was for sure, and then x equal to 5 and a is equal to 15. Every time we add information, we knew for sure it was okay. Because we started everywhere with the worst possible answer, which is nothing, which is the empty set. And crucially, the place where it really matters is on these back edges. So optimistic iterative data flow analysis allows you to go down inside of a loop and assume that the back edge will give you really perfect information so that you can propagate whatever information you have coming in. And then you do the analysis and you see if you're consistent, and if not, then you iterate on a better approximation of what that information is, versus the pessimistic way of doing it says, I don't know if I'm going to even get, I don't even know if I'm going to get to reach the final analysis of this thing, because I may be stopped anywhere. And so I'm just going to assume that this back edge is the worst information, which is the empty set. And this empty set is always going to remain the empty set, and it's always valid. Actually, no, that's not true. It may not, it may actually change. In fact, actually, this empty set may change. This empty set could change if you have an assignment here. For example, if you have, like, for example, b is equal to 10, then this thing could change to b is equal to 10. But then it doesn't matter, because you would do the intersection. And this is true. Right after the statement, b is in fact equal to 10, right? So you could be stopped right in the middle, right here. You're done, and actually you concluded correct information. Right? So you're always in a correct state, essentially. I mean, in some sense, the way to think about this version of it is that you start at bottom, which is, at the empty set, where you have no information, and every time you add some piece of information, you know for sure that you concluded for sure that no matter what else happens after the analysis, it's going to be correct. Whereas in the previous version, we had this much more lenient thing. Actually, quite frankly, very scary if you think about it. But it all turns out okay. Where we conclude things that are completely wrong in the middle of our analysis, but then it all gets rectified and all gets pruned out as we kind of reach a fixed point. Okay, does that make sense? Difference from starting at bottom versus starting at top. Okay. Oh my God! Okay, we're done. Next Thursday, hold on. Next Thursday, no, in 2 days from now, we're going to talk about super optimizers. We're going to talk more about analysis, and then next Tuesday is you have to hand in your projects, right? So I'm assuming you guys have been working really hard all this time on your projects. And if you haven't, you just say yes, and then you go down and work really, really hard on it now. But the point is, you can hand in your 2-page document next Tuesday. One per group.